Okay, since we were looking at this absolute value function, let's go quickly also look at what that not being differentiable at 0 will translate to when we look at the graph of this guy. So we already know the absolute value function looks like a v, and we just found out that it's not differentiable at 0. We proved it, and we also talked about it earlier that if there's a sharp corner, there is going to be no derivative at that point. So f prime of x, let's look at the graph of that. And if I'm trying to do what I did earlier to get the graph of the derivative from the graph of the original function, this is just a linear function. On the right, the slopes are always equal to 1. On the right side, a positive 1. And the slopes are always equal to, I guess, a negative 1 on the left, because it's just a basic linear function. So if I'm graphing the derivative on the right side, to the right of 0, I'm just going to get 1, because the slope is always 1. And on the left side, the slope is always negative 1. So that's what the derivative will look like. And right at 0, we said it's not differentiable. So right at 0, I'm going to not define the derivative since it's not differentiable at that point. So I'm going to leave open holes. And of course, we showed earlier above too that the derivative is just 1 if x is greater than 0, and negative 1 by doing the limit analysis if x is less than 0. We're not including 0 anywhere because at 0, again, it's not differentiable. So we also have the idea of continuity and differentiability related to each other with a theorem. And the theorem basically says that if f of x is differentiable at a, then it is continuous at a. In other words, differentiability is a stronger argument, meaning differentiability implies continuity. For example, let's look at our f of x equals x squared function. We showed earlier that this, the derivative for this is 2x. We used the definition, so it's differentiable for all x. This, by the way, means for all. It's differentiable for all x, so it's continuous for all x as well. In other words, if you can show differentiability, continuity is automatically implied. Now the question is the converse of this theorem true? In other words, does continuity imply differentiability? If I have a continuous function, is it automatically going to be differentiable as well? Well, no, because we just showed one case, right? So this wouldn't be true. For example, we looked at the absolute value function, and we know that function is continuous everywhere. I don't lift my pen at all to graph it, but it's not differentiable at x equals 0. So continuity does not imply differentiability, but the other way holds. In other words, differentiability is a stronger argument. Continuity already comes with it. Let's look at the notion of higher derivatives. Well, so far, we've looked at the first derivative. If I have f of x, if I take its derivative using the limit definition, for example, I get f prime of x. For example, we looked at the basic x squared function, and we went through the limit definition, and we found that f prime of x is 2x. Now, this in itself is another function. So if I wanted to, I could apply the limit definition and get the derivative of this guy, which would give me the second derivative of the original function. In other words, I had a function that gave me a derivative who's also a function. Now I can take the derivative of the second guy and get another function. So once I put that in my 2x function and simplify, looks like these guys cancel and the h's cancel, and I just end up with 2. In other words, if the function is x squared, its derivative is 2x, and its derivative, meaning the second derivative of the original function, is 2. And with this idea, we could keep going, and we could find the third derivative, which we can already guess, since we know this is just a horizontal function. The slope is always going to be 0. We showed that earlier. The third derivative of this function would be 0. So we could have the derivative of a derivative As long as I keep getting functions, I can just keep going through them as such. Now, how does this relate to a concept we've looked at before, which was position and velocity? We had looked at this idea earlier that if s of x is the position function, and we look at the change in s over the change in t, and we make, of course, t go to 0, keep making the time interval smaller and smaller, we would get s prime of x, which would be the instantaneous velocity. So instantaneous velocity function was just the derivative of the position function. We'll call that v instantaneous. Now that we know the idea of second derivatives, we could potentially take the second derivative of this original position function, which would really just be basically, if I call this guy, let's say, my velocity function, would be the change in velocity over the change in time. And as I make the time interval shorter and shorter, if you recall, the change in velocity over the change in time actually gives you acceleration of the object. So this function is actually going to end up being, I'll call it a instantaneous. So to sum it up, if s of x is the position function, we will have the derivative of the position function always be the velocity function. Of course, instantaneous velocity, velocity at each point. And the second derivative will always be the acceleration function, which of course we're talking about the instantaneous acceleration. So at a moment, what is the velocity of the object? So how much does it gain or lose in position per unit of time, and acceleration in that moment, how much is it gaining or losing velocity? Now let's go look at the examples that we were going to do in class together. So after the lesson, hopefully this example shouldn't be too hard. Maybe we'll look at a couple of them. I go to the each input, each x value given, and I try to guess what the slope of the tangent line is there, because I'm supposed to estimate the derivative, which to me really just means m sub tan, the slope of the tangent line at that point. So let's go stand at -3 and kind of guess. So at -3, I have definitely a negative number. You know, you can make a little triangle and guess if it's asking for an actual number, like maybe a negative, a half, or -1, something like that. So I'll make an XY chart and just guess some values. At -3, it was like maybe a negative a half. It's even smaller probably because it's not that steep. At -2, so that's -2, it looks like the slope of the tangent line is horizontal, so that's going to be a 0. At -1, if I make a tangent line and guess the slope, that could maybe potentially be a +1. If I'm looking at that little triangle, 1/1, again, these are just guesses. At 0, it looks like also it may be close to 1. It looks similar to the other one, although it's looking a little bit steeper than this previous one. So maybe I'll just go ahead and make this like, I don't know, 0.8-ish and say that this is about 1. Again, they're all guesses. And at 1, I have this whole symmetry business going on. This one looks kind of the same as this one maybe. So at 1, I'll say, I guess that's about 0.8. This is the same as this. Then we get to 2, and again, we have a horizontal tangent line, so the slope is 0 there. Then we get to 3, and that's definitely a negative slope, and it looks like the same slant as this guy over here at -3. So I'll say maybe that's a -0.5 again. And with this little chart, I can go ahead and maybe guess and see what the derivative function may look like. And all I'm doing is just plotting these. So I'm doing them point by point. So I plotted these x coordinates and these y coordinates, which were really the slopes of this line or curve. And once I connect my dots, maybe my original or my derivative function would look something like that. And again, notice the 0 slopes smack in the middle, and the negative slopes along the edges with the negative values, and then the positives up here. Let's go look at the next example. And again, this also is guessing a sketch of the graph below it, but this one was really in detail, point by point. We got a guess for the y-coordinates. Here we're just going to try to get a sketch. So we'll start off with the easy point at 0. The slope seems to be 0, so I'll get that dot going. And on the left, I have really steep positive slopes. You know, they're pretty steep. As you go down at the beginning, they're not as steep. They're positive. It's like this. Then it becomes more steep, more steep. So as I go to the left, the slopes keep getting bigger and bigger. I'll guess something like that. Positives, they're all positive and they keep getting bigger and bigger. On the right, notice they're negatives and they keep getting flatter and flatter, which means negatives, but going towards 0, a flat. The flatter it gets, the closer to 0 it gets. So my guess is on the right, I have negative values, but I don't keep going down. The negative values become closer and closer to 0. So that would be my guess for the derivative from the graph given. And let's go look at the last, or second to the last example. And this is pretty quick, not differentiable. Sharp corner, not differentiable. Discontinuity, not differentiable. Discontinuity, not differentiable, and sharp corner. So based on the 3 cases we talked about in the notes, that's pretty self-explanatory. At -4 and 0, at -1 and 2, these functions are not differentiable. Last one shows the position function of a car, so our s of x, the velocity of the car, and the acceleration of the car. And we have to figure out which one is which in this case. So let's go analyze each one. All right, so remember horizontal tangent lines are quick and easy to spot. I'm thinking there's a horizontal tangent line and there's a horizontal tangent line, but none of these graphs, neither B or C, is 0 there. So none of these can be the derivative of A because none of them have a 0 there. They don't go through the t-axis. So A must be the acceleration because I don't see its derivative as B or C. Hopefully that makes sense. Okay, next. So hopefully this explanation made sense. I'm just focusing point by point, the easy things I can see. The other thing I notice is that when I look at the horizontal tangent line of B, that's actually where A is 0. So it looks like A must be the derivative of B, because also when I have B have positive slopes, A is positive, and when I have B have negative slopes, A is negative. So if B prime is A, then we must have that B is the velocity function, which means that leaves us as C being the position function. And let's just go see if that kind of coincides well with the B. In other words, is the derivative of C equal to B? Is the position function differentiated giving you B? And if I look at it here as far as slopes are concerned, these all have positive slopes, which does B also. B is positive on that side. Then I reach probably my maximum slope. Then it stays positive, but it flattens out, which is described by B. It stays positive, but it flattens out and approaches 0. So all 3 tie in together, and it makes me lead to the idea that C is the position function, B is the velocity function, and A is the acceleration function.